And so I'm going to talk about the performance of quantum SDKs. I want to start my talk by putting this in. We're going to talk a lot about software, but I'm going to start by talking a little bit about the context of our industry and some recent hardware developments also at IBM. I think maybe one of the unfortunate stories about quantum computing in the industry so far is that despite marvelous advances in hardware, what people are doing with it in practice is maybe less than you might hope. There was a group of collaborators in Japan, led by Yoshikawa at the University of Osaka, that cataloged all the research papers that use quantum hardware and computed the average number of qubits used in these papers. And what you see is that people are not using very many qubits at all. In fact, they're using so few qubits that they could have simulated the results of those experiments using classical hardware and not fancy classical hardware that the NVIDIA Grace Hopper GPUs that we mentioned this morning. But in fact, even the Intel 8088 processor of IBM is really wide open sufficiently for all these simulating the results of all these experiments. And if you sort of extrapolate on this trend, you can see that we'd be waiting a very long time before we were starting to execute things that you cannot trivially simulate with a classical computer. And of course, I'm not patient enough to wait for 2036 to actually have an impact on the world. I'm looking for a disruptive change that changes this trend and has us start to investigate and do things with quantum hardware that I can't do classically. Fortunately, though, this trend has changed. And for us, the moment that sort of marked the transition point was this paper that our team published that showed that a quantum computer could calculate accurate expectation values in a regime that was beyond brute force classical simulation. We could just do a state vector simulation of the It turns out that there are other ways to simulate this experiment with more clever simulation methods. But this kind of was the beginning of, it broke the dam in terms of people's willingness to do experiments at a scale that we call utility scales quantum computing. And so even just 1 year later, we're now seeing a lot of work finally looking at scales which use substantially more qubits, including all these papers, and the list keeps growing. There was another one earlier this week that I haven't had a chance to after this list. And that means, though, the trend line is changing. So adding a few data points to this curve of publications now using IBM's Eagle processor or Heron processor, we see that we've broken the trend. People are finally starting to work at scales beyond what can be simulated with classical simulation. So if you haven't yet joined this bandwagon, I encourage you to break free of your classical simulation restraints and enter this wonderful world of utility scale quantum. One of the things that has enabled this change is advances in hardware. Right, the IBM Heron processor, as kind of its stats part, is shown here. Right, we often talk about performance of computers in terms of these three critical metrics of scale, quality, and speed. The second generation Heron processor has 156 qubits. The error rate measured in 100 qubit chains is 4 times 10⁻³ The best 2 qubit error rate on we've observed is 10⁻⁴ now, and these systems are very, very fast. We measure speed in terms of second layer operations per second, and this is a metric which when we first started measuring it, we were seeing CLOPS of about 1,000, which is already several orders of magnitude faster than most of the speeds that you can get with other qubit modalities. But through a couple of years now of software engineering, we've managed to squeeze out much more speed from these systems, now approaching something more like the intrinsic gate speeds available on the hardware. In fact, we can go faster. We're basically approaching now, we're limited by basically state initialization, how quickly we can recreate a fresh zero register. These gate error rates, though, are basically the result of iteration. Fastest cycles of iteration. If you look at the mean error rates on all the systems that IBM has put online since 2018, you can see there's kind of this general downward trend in mean error rates. The last few systems I've plotted 2 data points representing not just the mean error rate, but also the best error rate on those devices. And you can see that there is a substantial gap that remains, but some of our newest systems have employed technologies which allow us to greatly shrink that gap. And what is more or less happening because our latest systems are coherence limited. We've managed to squeeze out most of the coherent error in the devices. And so what you're really observing in the sort of difference between the best and the mean has to do with the distribution of coherence times of the devices. But our latest generations of Heron also now include basically in situ tunability of 2-level systems, allow us to modify the local environments of the qubits, and that allows us to change the distribution of coherence time of the devices. So that's why when we look at these effective error rates, the Heron devices look distinctly different from the processors that existed before. So even just going from our 1 generation of IBM hardware from Eagle processors to the Herons, you can see there's about a 16-fold improvement in error rates. Okay, so but I promise that this is not a hardware talk, right? Hardware is not the full story, but we are entering a new era where we really need performant classical software to unlock the full value of hardware. And the reasons for this were eloquently described by Josh this morning, right? When we're looking at these circuits of larger scales, we suddenly care and notice about unique defects in our software, right? The runtime and memory use that it uses to represent and compile circuits, and suddenly manifests directly when looking at these larger scales. So it's really kind of the improvements in quantum hardware that have made us care a lot more about the performance of our kind of software. So I want to tell you about performance then of Qiskit. I don't think I need to introduce Qiskit to you, but maybe a few interesting stats that Qiskit is very widely used in these unitary fund surveys, which were also mentioned this morning. Well over half of the respondents identified themselves as users of Qiskit. And I would say it's a thriving open source project, right? About 3/4 of the contributors to Qiskit are non-IBMers, so we also have a lot of involvement in the community in this piece of software. Qiskit had its 1.0 moment earlier this year in March, kind of announcing that we felt that Qiskit had arrived at a sort of a new stage of maturity in terms of its reliability, its stability, and its performance. But really, Qiskit 1.0 was just the beginning of it's kind of the first checkpoint, the first milestone along the journey to improve performance of Qiskit. So I want to tell you in the next 10 minutes or so about what has kind of driven the performance of Qiskit of late, what we've done since Qiskit 1.0, kind of coming up into 1.0 and beyond, and sort of where we're going. So the kind of underlying engineering strategy that we've taken to improve performance of Qiskit is to basically have Qiskit be reborn from within. Right? Qiskit started out as a pure Python framework, pure Python library, but we are re-engineering Qiskit's core and Qiskit's internals to be a 100% Rust library, high-performance Rust library that maintains a thin Python interface layer so that users of Qiskit interact with it the same way, but they are getting a performance upgrade from this conversion of its core to Rust. And in the Rust community, this conversion is called oxidation, which is kind of cute if you have encountered that before. But the Rustaceans are very passionate about their project. You might ask why Rust and not some other high-performance language. And it's not just because it's fashionable among software developers. It actually really has some real benefits. In particular, this guarantee of memory safety is something that Rust delivers with no runtime cost, which is somewhat remarkable. It's one of these programming languages, if you haven't used it before, it's one of these programming languages where, as the developer, you go to battle with the compiler, right? It is difficult to get a Rust program to compile. You get all these error messages from your compiler telling you about all the different ways you've done something wrong. But when it finally does compile, you're guaranteed that many of the mistakes you could have made are not present anymore, because the language, by its structure, prevents you from doing it. So you paid the cost as the developer up front before it compiles, and then that costing gets removed so that you still have a high-performance execution at runtime. And one of the other beautiful things about Rust compared to something like C++ is that the tooling and infrastructure that's around it is very, very pleasant to work with. The create system, there's built-in ways to do benchmarks as sort of part of your build process. There's just a lot of really, really convenient tooling around Rust. In particular, one of the things that's been done very, very well is this idea of being able to compile a Python C module from Rust code is something which is very, very cheap with Rust, making this integration of a Rust core inside a Python framework actually pretty seamless. So where did we start in terms of this project of upgrading Qiskit's internals to Rust? The very first thing we looked at was one of the core data structures of Qiskit, which is the directed acyclic graph. So Qiskit represents quantum circuits in the course of transpiling them with a DAG. And so you have basically all these transitions from your operations and measurements operating on the qubits. And any kind of transformation that you're doing in Qiskit is really a transformation of a graph. Whether that's doing something like a basis change, where I'm going to be iterating for like a topological sort of this graph, or gate optimization, which may have to do with collecting and replacing different nodes. Basically, every operation of the Qiskit transpiler involves a manipulation of a graph. And so Qiskit was using the very, very popular NetworkX library in Python. This is not a unique choice. Basically, every other SDK uses the same graph library. But what we did was to basically make a Rust re-implementation of NetworkX. Again, exporting a NetworkX compatible interface into something that's called RustWorks. So RustWorks is kind of an independent open source project. You can pip install it as well. And if you're using NetworkX, you can probably pip install RustWorks instead and have most of the APIs just work out of the box, but with substantially better performance. We haven't done 100% coverage of NetworkX. It is a large library, and it changes quickly because a lot of graph algorithm research lands in NetworkX very, very fast. So of course we implemented the things that Qiskit needed and a little bit more. If you would like to expand RustWorks, we're always happy to take contributions. But you can see some of the performance benefits in these benchmarks on the right, where the NetworkX performance is the orange bars, and RustWorks is in blue. And you can see that the transition to Rust really did pay off in this case. So that's where we started, was with this replacing the kind of fundamental graph data structures used by Qiskit. But there's a lot more to Qiskit than just graphs. One of the largest pieces of Qiskit in terms of computational cost has to do with the transpilation passes. And Qiskit has a very flexible pass manager, letting you build kind of multi-stage networks of transpiler pipelines. In fact, the sort of the default optimization pipeline in Qiskit is optimization level 2, and that includes 50 different passes as part of just that pipeline alone. But if we're looking at these passes when we're also looking at utility scale circuits, you can see that we have many operations that need to be done to optimize just a single circuit. For instance, on a 100 qubit QAOA circuit, we counted that we need to do over 2.5 million operations to optimize this with Qiskit's default optimization level 2. So any sort of iterative thing in Python is going to be slow. So obviously the next major challenge was addressing Qiskit's transpilation passes themselves. And so the kind of journey we've been on then, in Qiskit 1.0, basically the only thing that had been converted to Rust was this graph data structure. By the time we got to Qiskit 1.1, we had started to introduce, we'd also converted to Rust numerics for some of the manipulations of the most expensive passes. By the time we got into Qiskit 1.2, we now had complete Rust data structures for the quantum circuit model itself, so that all the data is stored in some sort of Rust object. And basically what's been left, well, so that already on this particular benchmark, a unitary synthesis benchmark, had yielded a 60-fold speed increase. But basically what is then left is then converting all of Qiskit's transpiler passes also to Rust, which is what we're doing with Qiskit 1.3, which will come out. So with all this work on improving Qiskit's performance, we really want to know, how did we stack up? How is Qiskit doing with respect to other SDKs you might use for building and optimizing quantum circuits? And to answer that question, we developed a new benchmarking tool called Benchpress. So Benchpress is available on GitHub. We've published a paper on the archive preprint server in September. And it basically is trying to cover not application benchmarks, but really benchmarks that are that cover the space of building and transpiling and optimizing quantum circuits. So it's if you want the pre-processing phase of using a quantum computer before you proceed to execution. Benchpress is mostly derived from assembling what we saw as the best of breed benchmarks that are out there. In particular, over 1,000 of the 1,066 benchmarks in this suite are derived from Bench, Feynman, and Hamlin, which are all other open source or academic projects that describe benchmarks for these tasks. And we've really kind of recast them, reset them in a language that allows us to test many different tools in a consistent way, and to also test the performance as we vary things like the topology of the system you're compiling for. We've implemented this test suite in a variety of different commercial and academic SDKs, including all the ones you see here. I already apologized to the speakers this morning because it didn't include, our list of what we've done so far doesn't include Q2Q or PennyLane yet. But if you'd like your tool to be listed here too, we're very open to expanding this test suite. All it takes is a wait for it. Obviously, we're at IBM very familiar with Qiskit, and you're less familiar with these other tools, so this was a wonderful opportunity to begin to explore what else is out there in the quantum software landscape, And one of the first things that we noticed is that different tools are really not trying to solve the same problems, right? You notice, particularly among the things that are labeled SDKs, that you have some that really focus solely on the space of circuit creation and manipulation, and some of them can do it very, very fast. So like Circ, for instance, has an extremely compact data structure for representing circuits, and so its memory footprint is phenomenal. It's so good that when we first did it, we were like, are they really storing circuits in that representation? But it doesn't really look at this problem of circuit optimization. Right? Whereas other tools really have minimal infrastructure to create circuits. Really, the STACK project is a project from Amy at the university. He created it while at the Institute for Quantum Computing. Really, it can only import circuits from OpenChasm, and basically all the tool really focuses on is circuit optimization. So there's really only 3 tools from the ones that we've implemented that really are at the intersection of both of these use cases. And in addition to Qiskit, that's Ticket, and also Qiskit from Lawrenceburg for the National Lab. One of the ways that this manifests itself in the Benchpress results is that in many cases, we were unable to implement a particular test in the Benchpress suite in that SDK, which more or less manifests in a skip in the results of our testing. Right, so Circ and Bracket are showing up as skips here because they really focus on circuit building, not transpiling optimization. And STACK, again, it's the reverse, right? It focuses on transpiling. So the ones, it's maybe a curiosity of my colleague Paul Nation, he designed 22 of the tests that are not possible to pass in principle. You may ask why they're in the test suite, but basically it's compiling a circuit against a target, which the target has fewer qubits in it than the circuit use target does, so it's not possible to pass those tests. Let's look at some of the results. So if we focus specifically on the transpiling or circuit optimization tasks of the Benchpress suite, we noticed that the predominant distinguishing feature of how different SDKs did was related to the topology that we are compiling for. So this chart, which is from the paper, sort of breaks down performance on different geometries, whether they're linear connectivity or all-to-all. And what you're seeing on each one of these charts is a description of either you have gate count, circuit depth, and runtime of the compilation task, where Qiskit's value is the x coordinate for each dot, and the other tools are represented as its position on the y-axis. So a tool outperforming Qiskit is a dot below the dashed line, and a tool where Qiskit's performance is better is above it. And so there's a number of things you can kind of notice from this, right? I mean, one of the things that's immediately apparent, right, is the trade-off between time and circuit quality, right? So if we look at the green points, for instance, here, this is from the tool stack. You can notice that it is generally faster than Qiskit. Most of the dots in the runtime column are below the dashed line. But in terms of circuit quality metrics, right, the fact that STACK is spending less time compiling is evident in that the circuits it produces are lower quality in terms of both in terms of circuit depth and gate count. There is one tool, one set of dots that are producing better circuits consistently, and that is, you can see here, it's QTS, that's the Qiskit Transpiler Service, which is a new AI-powered compilation method, which if I have time, we'll spend a few minutes on. But I mean, the main take-home is excluding another piece of Qiskit itself. Qiskit is producing better circuits faster than the other tools that we tested in this suite. In particular for Ticket, which was its closest competitor, it's 13 times faster to produce circuits with 24% fewer TTP gates. If we just zoom in, you can see a little bit better here. These are just some of the heavy hex results. but you can kind of see in more detail what's going on. In particular, the red dots I've mentioned here is basically, you can see we're kind of hanging below the line for the Qiskit transpiler service. Most of the other tools are hanging above the line. This is data that we took in September, beginning of September. Of course, the software ecosystem is constantly changing, right? So the results really measure how things are at any one moment in time. And so, right, like the results in some ways are immediately out of date as soon as you publish them. But you can see a snapshot of how Qiskit is doing relative with respect to itself, looking ahead towards Qiskit 1.3, where, as I mentioned, most of the work now is about converting the transpiler passes themselves to Rust. And so if you look at how Qiskit is doing on all 10,066 tests in the Benchpress suite, we're seeing an average performance gain of about 2.2 from this next phase of Qiskit's performance project. All right, so what's the take-home message? Out of the box, Qiskit has fantastic performance, but in fact, you can do more. And the way you can do even more is through Qiskit's plugin infrastructure. One of the lightning talks right before lunch mentioned this as well, right? But Qiskit is has a compiler infrastructure which is pluggable, right? For all the five different stages of the Qiskit pipeline, which has initialization, layout, routing, translation, optimization, and scheduling. Actually, all Qiskit's transpiler passes are built as plugins to the transpiler pass infrastructure. And the ones that are sort of the best passes end up actually being migrated into Qiskit's core. But at any different point, you can plug in and introduce things which are sort of out of package. And so to give you a few examples of this. So one example is there's a plugin for a package called Rustic, which is developed by Simon Martia. And what Rustic is something which is particularly good at synthesizing circuits that are kind of relevant to Hamiltonian simulation. So if you have like a time evolution circuit of a Hamiltonian, Rustic has a synthesis algorithm which can produce particularly good circuits for that kind of structure. And it's, I don't have time to go into the details of how it does it, but basically what it tries to do is synthesize a circuit which consists only of 2 qubit interactions plus a final Clifford operation, a generic Clifford operation, recognizing that this final Clifford can actually be absorbed into the interpretation of the measurement, so you don't actually have to implement it physically. And so this can lead to very, very efficient synthesis for Hamiltonian simulation circuits. The AI passes that I mentioned with the Qiskit transpiler service is also pluggable into the same infrastructure. So if you just want to use the AI passes for routing, you can do that. Like also in one of the lightning talks you mentioned, this is based off of a reinforcement learning technique to automatically recognize, to basically train a neural network model on patterns for improving circuits. And so this particular technique turns out to work well on circuits get larger. It's patterns, it can find effective patterns, particularly on large circuits. We're seeing about another 24% reduction in 2 qubit gates once we get to the 100 qubit scale. And we also have things that can do, for instance, recasting a synthesis problem into a Boolean satisfiability problem, converting a kind of an oracle into conjective normal form, and then using a SAT solver. This is a technique which is sort of exponential in the generic case, but for finite sizes can yield optimal synthesis. So, out of the box, you can get a good experience, but if you really know what kind of circuit you're compiling, you can choose, you can expand the Qiskit transpiler pipeline with plugins. that can improve its performance. So here's an example of doing a Fermi-Hubbard simulation, so another Hamiltonian simulation problem, but where if you plug in this rustic pass for synthesis, you replace Qiskit's default routing pass with AI-based routing, and you use this people optimization with the set solver. You can see you can improve the gate count and depth of the circuit compared to Qiskit's defaults. Just one more word about this transpiler, this AI transpiler. If you are currently an IBM Premium customer, you have access to this today. It's just flip installable, available as a service. But then later this year, we will be releasing local versions of these models on your laptop, which will be available to everyone. And that's effectively been made possible by shrinking the sizes of the models so that you don't need kind of a bespoke infrastructure in order to run inference on them. Okay, so I guess just to wrap up, Qiskit really has the performance to unlock the next phase of exploration in quantum. I hope if you've had the impression in the past that Qiskit is a great tool for learning, but it's maybe too slow, I want you to take another look at Qiskit because all the work that we put in the past year has, I think, really changed that story. Thank you.